Alrighty, welcome back to operating system. So, everyone love page tables now? Yay! What was that? All right, that wasn't me. So, today we're just going over page tables again. So, here is how virtual memory gets translated. So, any questions, comments, or concerns before we dive more into it today? Or did everything last lecture more or less make sense? AKA yesterday. Yeah?
So when you get the page table entry from L2 that points to L2, does it point to the base of the L1 and then you use the 9 bits that are allocated in the virtual address to index into the page table, or how does that actually work again?
Yeah, so you do use the bits to actually figure out which index in the page table you need to actually access, and you're given, right, there'd be a register, something keeping track of the root page table where to start, and then you can figure out the rest from that. And we'll see more examples today because it needs to be stored somewhere. So we'll do some more examples just to make sure this is all clear. All right, more or less okay. All right, so first thing I will talk about is something called alignment. So you might have heard this term before. Basically, it just means that eventually all of your allocations eventually line up with byte 0. So if I say something like pages are 4096 byte aligned, that means all of the lower 12 bits, all of those 12 bits will always start with 0. So no matter what the address is, it will be essentially divisible. If you just take the whole address, convert it to a number, and then divide. Aligned means that everything is divisible, and computers like alignment because it's very easy to figure things out. So if instead my pages were not aligned, then maybe I have a page that starts at address 7C00, aka one of the 12 bytes. It's like starting somewhere within a page. Well, if I start at address 7C and I have page number of bytes, so I have 4096, which means I would have to add 4095 to the number. It means the last byte of the address would be 8BFF, which is not great. But because pages are all aligned, so they'll start in a multiple of 4096, page, I would just say it's on page 7, and then it would immediately, I know the lower 12 bits I can immediately just use for the offset which byte on the page I need to use. So the pages would start at the address 7000, and the last byte would be at 7FFF. So you can verify that that is a page, but that's why we don't need to store the offset or anything as part of the page table entry or anything like that, because all of the pages are page aligned, so we know exactly where they start and where they end. So since we just take the address and we essentially say it's aligned, if it's divisible by that number, say I have the address EC, so that is a memory address EC, I might be asking you things like, hey, is that 8-byte aligned? And what would you tell me? Is that 8-byte aligned, yes or no? Which means, hey, if that is our address, is it divisible by 8 without any remainder or anything like that? Is it yes or no? See some yeses? Yeah?
No, it's not.
No, why?
Because C is not divisible by 8, so I brought the rest of it not.
Yeah, so C, so the response was, hey, it is not 8-byte aligned because this is not divisible by 8. So since it's powers of 2, this represents like, you know, the 16 columns and all up there. That is also going to be divisible by 8, so I don't need to consider that at all. I can just look at the lower hex digit here. So if it's 8-byte aligned, it means that it ends with a 0 or an 8. So it will either be 0 or 8, the last bit, or byte, or sorry, the last hex digit. If it's 0 or 8, it's 8-byte aligned. Otherwise, it's not. So C is 12, not divisible by 8. So everyone okay with alignment? AKA if it's divisible. So that's why we don't need to store exactly where a page starts. We know everything's page aligned. So by having the PPN, just with the PPN, we know the whole extent of that page. All right, so we saw that simulating the MMU, we have that whole code example. We can keep that in mind. We showed it before. I made an L2 page table, I made an L1, I made an L0, and then I set the indexes to point to each other such that we could translate that address A, B, C, D, E, F, and if it's not able, if it fails at any step along that translation, the MMU that's actually using page tables to translate the address, it'll get a page fault. So we do have this example, it is provided for you, but any questions about this, I'll also be able to go back to it at the end. All right, let's just move on and do other questions first, just in the interest of time, and we can play with that later. So, a question for you to make sure we have understood things is, let's assume a process is, oh, we're going to do that again. I thought I fixed you. So a process is using 512 pages worth of memory. So if a process is using 512 pages worth of memory, one question I might be able, we're going to do this again. So one question I could ask is like, what's the minimum we're going to do this. Minimum number of page tables required. So anyone take a stab at that? So my process is using 512 pages worth of memory, and well, if I am the kernel, I need to make sure that each of those pages of virtual memory map to some physical memory so that it actually works. So how many page tables would I need to do all 512 translations for this process at minimum? 1. How would I get away with 1? $512, yeah, can't quite get away with 1. You could like do some recursive stuff and then get lucky, but yeah.
How many entries are there in each page?
Oh, so just as a reminder, we will be doing the default scheme we saw before where we have 3 levels of page tables. So essentially, here, I'll swap to the slide real quick. So yeah, just as a reminder, we are using this scheme where we have 3 levels of page tables, and each one can fit 2 to the 9 entries, or 512. So 3 levels of page tables, and each page table has 512 entries, or 2 to the 9. So we have that many entries in our page table. Each entry, just as a sandy check, is 2 to the 3 bytes. That is our PTE size. So the total size of this, just as a sandy check, would be 2 to the 12, which is the size of our page. So how many page tables do I need at minimum to translate 512 pages, which is to the 9? Yeah. 513 page tables? Why do I need 513 page tables?
One page table will like account for each page, and then the 513th one will be an index each of the like 512 ones in each page.
So I always have to have one L2. So I have an L2 and it points to the 9 L1s. So I have this, and then I have to the 9 L1s. And then what? That's it? So how many page tables do I need to translate a single address? Or 3, right? So here, let's back up a bit. So even to translate a single address, right, I would need one L2 page table. It would have one entry. That entry would point to one L1 page table. Then it only needs a single entry that points to an L0 page table. And then that could go ahead and point to whatever the pages I'm using, right? So the physical page number for this virtual page number to actually give me the translation. So I need 3 page tables at minimum to translate a single page, right? So if I had to translate up to 512 of them, could I still only use 3 page tables, or do I have to make more? Anyone, I need help. Yeah.
So yeah, what I think is that each page needs 2 to the 9 entries or 512 entries. Then having 512 L0 pages going to each like having like 512 like L0 pages would be leading to. Okay, I don't know.
So each page table can fit up to 512 entries by itself, right? So if this L0 page table was full of entries that pointed to things, and this is the page table that actually, it's the last level translation, so it's actually the physical page I need for this virtual page, then if that's full, how many entries are in here? 512. So if they're all full, all pointing to something, how many different pages is that? 512, right? So that's all I need. So in this case, the minimum number of page tables I need to do every single translation is just 1 plus 1 plus 1. That's 3. So I could, in L2, it just has a single entry that points to an L1. Then that L1 has a single entry that points to an L0, and then that L0 page table is full. So what would happen if I need to map another, I don't know, I have like a 513th page I need to use. Well then, at that point, I have no choice. That L0 page table is full, so I need another L0 page table, right? So I need an L0 page table, and then I need, and then I need an entry in L1 to point to it, right? All right, I hear rumblings. Is everyone okay with that? All right. Well, what about if I said the same question, what's the maximum? If I can spell maximum, number of. All right, what about if I was actually terrible at doing the mapping? What is the maximum number of page tables I have to use? 2 to the 27, no. So worst case, if I need to have translations for everything, I need 2 to the 18 different L0 page tables. But I only need to translate 512 pages. So that would be if I need to translate like 2 to the 18. Yeah?
Isn't it 512 times 512 times 512?
512 times 512 times.
No, or it's actually addition, because you have a one-to-one mapping for each of them.
Addition, so let's see. How many L2 page tables do I need? One, right? So I always have to have one L2 page table, no way around that. It's always just one. Because I need to know where to start. So I have one L2 page table. So you're saying that, hey, it could be full of entries, right? So it could be full of entries where every entry in the L1 or in L2 points to a separate L1, right? So how many entries are there in the L2 page table? 512, right? So how many L1 page tables would we have? 512. So worst case, each of my L1 page tables just has one entry in it. So each one just points to a single L0 page table. So they all have a single entry, ... So if I have 512 L0 page tables all pointing to a different unique L0 page table, how many L0 page tables do I have? 512. So in total, I need one L2 page table. So it would be 1 plus 512 plus 512. So the worst case to store the translations for 512 pages is I need 1,025 pages of page tables just to store that. That seems bad. Does that make sense to everyone? And also, you can tell why they actually picked the L0 as like being. So if we just look at the last few bits of an address over here. So if we just look at the last few bits of an address, right? If you're accessing memory contiguously, right? Eventually, this might be something 0. And then if I access memory contiguously and my offset, goes from 0 all the way up to full, and then I use the next page, well, this just increases by 1, which would make it go to the entry right beside whatever it used before. So if you use memory contiguously, you're more likely to be in this situation where all the entries are beside each other. Everything's nice. That's one of the reasons why they tell you to use memory contiguously, because if you didn't, and you're accessing a different page every time, especially if you get into this scenario at the bottom, you can waste a lot of space, because in this scenario, I'm wasting what? My program's using 512 pages, but I'm using over double that just in page tables if I've screwed up. While if I accessed everything contiguously, I'm more likely to be in this situation where I'm only using 3. We'll see other reasons for that too, but does this make sense? Some nodding. Okay, so another question we can do. There might be questions of like asking you to figure out how many levels of page tables I actually need. So I will Yeah, so I've discovered from the previous section, none of you are young enough to remember 32-bit processors, right? But back in the day, we had 32-bit processors, believe it or not, and it used virtual memory, had the same page size, so we should figure out how the system worked back in the day. So back in the day, let's just use some numbers. So back in the day, we had 32-bit virtual addresses. So 32-bit, that goes up to 4 gigabytes of memory. So each process can use at most 4 gigabytes of memory. And if it's 32 bits of physical as well, then we can only use 4 gigabytes of memory on our machine. So back in this day, we still had 4 kilobyte, or I'll just write in powers of 2, we still had 4 kilobyte pages. We're going to do that. Which is just another way I like to say the page size. And then, well, because we had less physical memory, right, we could get away with having a bit smaller page table entry. So we had a 4-byte, which is 2 to the 2, PTE size. Makes sense. We didn't have quite enough memory. We didn't need we didn't need 8 bytes of page table entry size. So back, they used the same thing, like each smaller page table fit on a page. So we should be able to figure out how many virtual pages, or how many levels of page table entries did they need, or sorry, how many levels of page tables did they need in this system? So first thing, if I give you all of this, the first thing you should try and figure out is how many PTEs, all right, looks like yeah. So first question is, how many page table entries can I fit on a page in this system? So anyone want to let me know? 2 to the 10, right? Simple. So if my page size is 2 to the 12, and each page table entry is 2 to the 2, I'm figuring out how many I can fit on each page. So I can do that. Whoa. The last room was fine. I don't know why this is so cursed. So this is due to exponent law, 2 to the 12 minus 2, which is 2 to the 10. I mean, I can write it out, 1024, whatever, it doesn't matter. So when we had that, remember we used some number of bits to figure out what index we had to use for our page table. So if I can fit 2 to the 10 page table entries on a page, how many bits would I need to be able to use that index and be able to select every single one of those page table entries? 10, right? Makes sense. Before, when my page table entry was twice as big, I needed 9 of them. And now it's half as big, so I need an extra bit because I can actually cram double as many page table entries on a page, since it's the same, it fits the same. So, that okay, that would be the number of index bits we have. So, if we have our virtual address, it always looks more or less the same. So we have our offset at the bottom. How many bits for the offset? 12, right? 12 bits, that comes from my page size. So that is what byte on the page am I trying to access. And then this whole thing was for the VPN. In this case, it is 20 bits. But if we use multi-level page tables, right, we have to break it off into different parts, and we have to figure out how many levels of page tables we have. So we start at the bottom, we have an L0 index, and then we figured out from here that our index bits was equal to 10. So this would be 10 bits here. And then, oh, well, that only gives us 22 bits for our virtual address, so we must need another one. So we must need an L1, and we must need 2 levels, and now we have, it looks like we only need 2 levels. So if you want a formula to figure out the number of levels too, you can calculate that the number of levels you need is equal to ceiling, whatever virtual bits, minus offset bits, all divided by index bits. And then you take the ceiling because, well, if there's any, I can't have like use half a page or anything like that. So if I need to support a larger virtual address that needs another level and it doesn't quite fit, I have to get a whole nother level, even though it might just have 1 entry. So that's why we have a ceiling here. But for this system, they designed it, virtual bits was 32 minus 12, or that whole thing is the number of total bits for the VPN. Then I divide it by the number of index bits I need, which is 10, and in this one, thankfully, it's a nice number. So it's just ceiling of 2 is 2, so I must need 2 levels. And that also makes sense because if I draw it out here, I can see that that gives us all of the 32 bits here. So if for some reason we wanted a 33-bit virtual address, well, it makes sense that we would need another level of page table. We would need an L2, and then our L2 would just have at most 2 entries to tell us which different L1 we should use, and then that would be full. So, that okay with everyone? All right, so this system has 2 levels of page tables. 64-bit machines, even with the 39-bit virtual address, use 3 levels of page tables. What is the practical difference between these two if we're using them? Or what will be faster? The 2 levels will be a hell of a lot faster, right? So, also before your time, fun story. When we first transitioned to 64-bit CPUs, they were slower because they had another level of page table primarily. And if you didn't have 4 gigs of RAM, so you didn't actually need that, your computer just ran slower for no reason. And then some people would argue, you do not need these newfangled 64-bit CPUs at all, because no one will have more than 4 gigs of memory ever, so why would you just want things to be slow? And people had to be dragged kicking and screaming into 64-bit, primarily because of this reason, well, it was slower. So, we will address some of the speed issues, but yeah, it is slower, and 32-bit machines were faster. Some people still support them. All right, any questions for that? Fun story time, right? All right, so we need to address the problem that even with 2 levels, 3 levels, we're still slowing down our memory quite a bit. And remember, we want using virtual memory to be almost as fast as using physical memory. So, you know, every single address, we need to follow pointers across multiple levels of page tables. It's awful. It is slow. You might also access the same page every time. So think of like using an array. If you use an array, it's likely every single element is on the same page. So you don't need to do the same translation over and over and over and over again. Your program might only use a few pages of memory at a given time. So the solution to speed this up is one of computer science's only solutions, and it is caching. So Oops. So there is a cache that essentially all caches do is save values and then retrieve them so you don't have to recalculate them. That's all a cache is. So there is a specific cache for doing the memory translations and looking up all the page tables and everything. And it is called a TLB, or translation look-aside buffer. And that caches PTEs at the lowest level at L0. So it tells you for the VPN, it actually saves the page table entry for this VPN. So it would match the entry in the L0 page table. And why it would do that is so you don't have to hop across L2, L1, L0, and all of that. So we would have our normal address from before. So if we have a 39-bit virtual address with a 4K page size, we have 27 bits for the virtual page number. This little table, it would save all of the translations for you. Well, not all of them, so this is of limited size, but this cache would be a hardware cache on your CPU that is meant to save your most recent translations, and the size of this would determine how many it can save. So if it has made that translation before, there would be something called a TLB hit. It would actually scan all of these entries to see if I have actually translated this virtual page into a physical page before. And if I had, well, it would store the page table entry, which has the physical page number and all of the permission bits. And then I would just use that immediately for my address. I don't have to actually access any other memory. The translation is already saved for me. I just use it. If that translation was not in this table, I have to, look it up, see if it's in there or not. If it is not in there, that is called a TLB miss, aka it is not present in the cache. And then we have to translate as I showed before. So knowing which L2 page table to use, I have to access an entry in the L2. Tells me where the L1 is. I access an L1 entry. It tells me where the L0 is. I access the L0 entry. Then it tells me what the final translation is. So if you went through that whole process, it would be saved in the TLB. So just a place to save the most recent updates. And then we would use it for the translation. So is that okay for everyone? We're not going to waste time. We want things to go fast. Yeah.
Does the same case apply to when we divide up the VPN into 3 sections, like the example above?
Yeah, so the 3 sections using the 3 levels up would be the translated using page tables. So that is the process that would actually be used. It's just slow and we want to save the result. All right, so TLB. So I had this come up during the midterm. Someone raised their hand and came to me and was like, asked me the question, what's a TLB? During the midterm. You should know what a TLB is. So that's not a valid question to ask me during a midterm. So TLB, this is what it is. A cache for all of the virtual memory translations to make things go much faster. All right, so to show that this cache actually works quite well, we will assume a single page table and figure out the effective access time, aka what is the average time to access memory. So we can assume that there's only one page table, so there's only one additional memory access if we have to look up everything. Of course, if we have 3 levels of page tables, there would be 3 additional memory accesses, but for this is just considering a single page table. So we have to calculate the time it takes to translate an address if it is in the TLB, aka TLB hit time, and the time it takes to look up an entry. It's not free. That cache is much faster than actual memory, but it's going to have to search, see if the entry is already there. So it's the time it takes to search and find the entry, and then we know where in physical memory we have to access. So we just have to do the original memory access in the case we have a cache hit. If we have a miss, if we have to go through the whole process, well, we have to pay the penalty of searching the TLB, not finding it, and then we have to do all the memory accesses. So if there's only one page table, we have to figure out we have to read the page table entry, and then we have to do the actual physical memory access. So we would need 2. If this was 3 levels of page table, this number would be a 4. So the effective access time, or the average, is alpha is the proportion of hits, so the proportion of cache hits, so times the TLB hit time, and then plus the proportion of misses times however long a miss happens to get our average time. So some numbers, a fairly bad rate is like, hey, there's a hit 80% of the time. It takes 10 nanoseconds to search, and normal memory accesses take 100 nanoseconds. Calculate the effective access time. Well, that would be 0.8, so 80% of the times there's a hit. So 80% of the time it takes 110 nanoseconds, so the original memory access plus the search, and then 20% of the time I have to search the TLB, which is 10, and then the 2 memory accesses, which is 210. So my effective access time is 130, aka it's 30% slower than using memory, which is a hell of a lot better than 4 times slower, right? So this is why it works. And this is primarily doing that translation, because you've been told so far that you should use memory contiguously, right? Has that not irked anyone before? Like, it's called random access memory. Why doesn't it all take the same amount of time? It does. So, why do they tell you to access things contiguously? To avoid this, so that if you access things contiguously, it's more likely they'll be all on the same page, and then it's more likely it won't have to do the translation over and over and over again, which is slow. Yeah?
Just wondering, so when we hit, why is the TLB time the same? Wouldn't the cache be like smaller so the TLB time would be shorter?
So it's the time to search the TLB too, so it's not free. So you need to look up the entry and see if it's there or not. So it's not free.
So like we just assume the memory to search, the time to search the cache table is the same as we do the memory access for the...
So the time it takes to search the cache is going to be much faster than memory. So here, the numbers I made up are...
The memory is the memory access.
Yeah, so here the cache searching is like 10 nanoseconds versus 100. So it's like 10 times faster. So it's worth it. All right, so this is, so that's primarily why the lie they told you of like just saying computers like contiguous memory, that's a lie. Everything actually wants to be on the same page for things to get fast, because all those virtual pages you use, if you cross the page boundary, well, one page might be here in physical memory, another page might be here in physical memory. They might be located very far away from each other, but because it's random access memory, they have the same speed. The only thing that's actually important is accessing the same page over and over again. So it's in the TLB and I don't have to look it up again. So now you can answer for the real reason why they tell you to access things contiguously, especially since it's called random access memory. I don't know if it irked anyone before, but it should have irked you a little bit. Yeah?
Wait, also just wondering, is the effective access time kind of just like the average time?
Yeah, same thing as the average access time. All right, so quick little note here too. So context switches, they actually involve handling the TLB because every single process has its own page tables, aka its own virtual memory mappings. Well, if I context switch between 2 processes, I also have to do something with the TLB because that is saving translations, maybe old translations for a different process. So if you context switch me in, I shouldn't use any of the cache values because they're only valid for a different process. So the options here, if you're the kernel, you have to make sure to flush the cache, aka you delete everything in the TLB, so that has to recalculate again for the new process. Or with some hardware, that TLB will also support attaching a process ID to each entry, so that if you switch processes, it won't try to use that cached value for a different process to save you from accessing its memory. Most implementations of kernels, whenever you context switch between processes, it just flushes the TLB. RISC-V, there's a certain instruction for it, sfence.vma. The VMA ones have to do with virtual memory. On x86, whenever you change the base page table or the root page table, that lives in a register, and whenever you change the register value, which would be done as part of a context switch, it immediately flushes the TLB for you, so you don't have to do anything. If you're the kernel developers, it's immediately flushed for you at a hardware level or zeroed out, and it's all gone. So let's go to a fun little example. So that's a bunch of writing. So there is this fun program to see the effect of the TLB in terms of memory accesses. Funnily enough, it was written by the same guy that started the Linux kernel. So this program, very, very simple, takes 2 arguments. It takes a size, so it will allocate memory of that size, and then it will access elements every stride bytes. So if stride is 4, it will access byte 0 of that memory allocation, byte 4, byte 8, byte 12, byte 16, keep on going over and over again. So if I do it with the argument, say I do this argument. So 4096, so I want 4096 bytes, which should be a page, and then I access every 4 bytes. How many TLB hits should I get, and how many TLB misses should I get? And first question you might want to ask yourself is, how many accesses happen, period? All right, here's some rumblings of right answers. Anyone brave enough to tell me what's going on? Yeah?
Doesn't it depend on the size of the cache?
Nope. Yeah?
2 misses, 1024 hits. 1022 hits.
1022. Why would there be 2 misses?
Because, so, first of all, there are 1024 accesses because...
Yep.
So 1022 accesses, each page is 512.
Each page is 4,000.
Okay.
Yeah, so that's one page. So very close. Anyone for the save? Yeah. Yeah, 1 miss at the beginning, right? So if I just have 1 page and I access 1,024 different elements, well, the first time I'm accessing a new page. That'll be a miss. I'll have to go through the whole process of figuring out which virtual page or which physical page is virtual page maps to. But all the other accesses, the other 1,023, are all going to be hits because they're all on the same page. I can reuse it over and over again, right? So, oops. So if I run this, each access, it takes an average of how long each access takes. So each access takes like 1.3 nanoseconds. So what if I do this? So here, this is a much bigger number. So this number is, I believe that's 512 megabytes. So I ask for 512 megabytes of memory, and then I access every 4,096 bytes. So how many misses do I get in this case? Every single time, every access is a new page, right? Over and over and over and over again. So should this be a hell of a lot slower? How much slower? A lot? 4 times? 4 times is pretty bad. 10 times? Well, let's just send it and see what we get. So it was 1.3 nanoseconds before. Ouch. So 30. It was almost 30 times slower accessing a new page every single time. So there's some more overhead associated with this because, well, behind the scenes, if we're accessing a new page all the time, the kernel actually has to allocate a new page for it, and a whole bunch of other things are going to go on, which makes it even worse than 4 times slower. The 4 times slower is just for translating the address, not to say anything about anything else going on, like allocating pages and figuring out where in memory they should go. So that is the reason to access memory contiguously. It is very bad if you have a new page access every time. So everyone cool with that? Cool little experiment. You can play with numbers and see smaller numbers will have more of an effect on caching, and you'll get different results. So another few things I can talk about. So we use a system called like that SBRK for user space allocation. That was a system called libc used to manage the heap. So malloc actually gets memory from here. So this system called grows or shrinks your heap. What the kernel will do is if you make this system call, it will just grab pages from the free list to fulfill the requests. The kernel would modify the page tables, set the page table entry as valid, set other permissions, and then point it to some new page it allocated. And for memory allocators, you might notice that like, hey, if I use a bunch of mallocs and then I free a bunch of stuff, my process doesn't use any less memory because it's typically, you can only shrink the heap from one end of it. So it'll stay claimed by the process. The kernel cannot free pages. It's really unlikely that you'll have like a page size empty at the very end so that the kernel can actually reclaim memory. So this is also why some processes that use malloc might look like they're using a lot more memory than they're actually using. So some memory allocators too, there's this mmap system call that we'll play with a little bit in the course to actually manage your own virtual memory translation, so everything doesn't have to be all in a row for virtual addresses. You can kind of modify your own virtual memory, and we'll see how that becomes useful later too. All right, so this is, you don't have to need all the details of this, but this is more explaining what happens in your process. So here, this is your process's virtual pages. So this is typically how a kernel will map them. So everyone's dereferenced null and got a page fault, got a seg fault before, right? How does that work? Well, the kernel makes it so that virtual page 0 is always invalid. So that whenever you dereference null, which is just the number 0, that would hit page 0. If there's no translation, you get a seg fault because it has no valid entry. A kernel could really screw with you if it wanted to. There's no reason why it couldn't map page 0 to some physical address, and then when you dereference null, your program doesn't crash anymore. Probably not the best thing to ignore errors and things like that, but you could do that. But the way Linux sets up things and most operating system things, page 0 will always be invalid. So that if you try and dereference null, it'll crash immediately. Then there might be some pages of instructions, some pages of data. Your stack would actually be a set size. And there's a trick we use because we've probably seen Stack Overflow before, right? Seen Stack Overflow? Well, how did the operating system differentiate a Stack Overflow from me just using memory invalidly? So stacks will be a set size, so they'll be using some pages. And what they do is at the bottom of the stack, they will make something called a guard page. So it is just right at the boundary. So it's a known invalid page. If you overflow your stack, it's very likely you will hit this guard page. And because it's a known page, it will just say, stack overflow, you likely overflowed your stack. And that's also why, has anyone ever overflowed their stack so bad they just got a seg fault instead of, so if that has happened to you, I believe it's happened to me before, if you have definitely you definitely had a stack overflow, but you just got a seg fault, what could have happened is you just jumped straight over this guard page. So you overflowed more than a page, in which case you just got a normal seg fault and then it just died. So you can Stack Overflow so bad that you don't even get notified of a Stack Overflow. And then the other information there, not important, more for the intricacy of like the kernel having to manage your process with its own virtual memory and manage yours and doing context switches. So we can forget about this stuff for now. It's not that important. The main thing is the guard page there. And like before,